Hi again, everyone. So today we are back talking about the derivative. This time we're going to get a little bit more about the derivative as the concept of a function as opposed to the derivative at a specific point. So we're going to go a little bit more general as opposed to the specifics that we were talking about yesterday. All right, so let's jump right into a definition. So this top part, don't write down because that was the definition that we had yesterday. So these two definitions, this is f prime of a for both of them. These are the derivatives at a point. So these guys, oops, these guys are derivatives at a point. So at a point. Um, Typically, this formula right here is something that we're going to want to use when we don't have a point. I mentioned yesterday, this is the formula that we're going to want to use if you're given a point. This one is a little bit more long and drawn out. But now we have this idea that we may not have a point. So what if we're just looking for the general derivative? So I kind of alluded to the fact that maybe when we're taking this example right here, and we're doing the longer version, we will get an answer that isn't just a number, right? We'll find something that is, I believe we had an answer, it was like 2a plus 4 or something like that for our answer. And I said, for whatever number you plug in for a, that is the slope or the derivative at that given point, because we remember that slope is derivative, derivative is slope. So now we can actually consider the derivative as a function. So if we're just considering f of x, we can find f prime of x, which is the derivative at any given point. So this is the formal definition of the derivative right here. This is the definition we are going to be using pretty much for the remainder of the class, unless we're given the derivative at a specific point, in which case, if you wanted to use this one, just because it's a little bit easier, you can. I apologize if you hear a little bit of whining in the background. My cat is upset because he likes to sit with me while I work. That's not happening right now. So this is the definition that we're going to be using for the rest of today and probably more or less the rest of the course, barring when we get to the rules, which will be the fun part. All right. So this again is just the definition we just had, so we don't have to recopy that down. But now we get to this idea of differentiability. So we have this idea of a derivative. When we take the derivative, we get a slope, right? So we can be differentiable at a point. And what it means to be differentiable at a point is just that the derivative exists. Now, the derivative does not necessarily always exist, in which case we would not be differentiable at a point. This also says like a couple different definitions. So it says it's also differentiable if at every point in an open set, the differentiable function f prime of x exists on its domain. My suggestion is we're just going to think about it in terms of if a derivative exists, then it is differentiable. And we'll go over some examples of what exactly we need to look for to know whether a function at a point will be differentiable or not. There are specific functions that will just have specific spots that we will know for certain are not differentiable. And there are other functions that we'll know for sure are differentiable everywhere. So we'll get there. All right, so let's go ahead and try an example. So now we're looking at the square root of x, and we're looking to find the derivative. And we're not given a point, we're just looking for the general derivative, and that means that we could find the derivative, which is the slope at any given point if we wanted to. So one thing that I always advocate for is rewriting or just writing the formula every single time because it helps burn it in our brains. So we have the limit as h approaches 0 of f of x plus h minus f of x all over h. This is the general definition of the derivative. I really hope you can't. He's running around like a nut job. Sorry. Now we can go ahead and actually pull this off to the side, kind of like what we did in the lecture video from yesterday, and plug it in. And then once we plug them in off to the side, we can put them back into the formula, and it really just helps make things look a little bit more concise. So f of x is f of x. The cool thing is when we were doing f of a, we had to pull it off to the side. With f of x, we don't have to do that. We already have it. So now we really only have to do f of x plus h. So f of x plus h equals, well, when you see anything in the parentheses, you just plug that in anywhere you see a variable. Well, the variable's only under the square root. So we have a square root of x plus h. And there's actually nothing we have to do. Yesterday, we were doing a lot of distributing. We FOILed a whole bunch. There's nothing we can do with this. So we can go ahead and just plug this right in. So again, we carry our limit through, limit as h approaches 0 of the square root of x plus h, now minus the square root of x. We don't need any parentheses because the square root of x is just a single term, all over h. All right, and now there's nothing that we can immediately look at and say, oh, I can simplify that. We see the limit is h going to 0. Well, the problem is that h is in the denominator. So one thing that I want to note very quickly is something that I also mentioned yesterday, is the idea that we're trying to kind of accomplish when we're doing this is we need to get rid of all of the terms that just have an x in our numerator. So all just x's, and I'm going to abbreviate the numerator as just numerator, num here. And the reason why we're doing that is because then we can factor out an h from the numerator and cancel it out with the denominator. So to cancel h out of denominator, then plug the limit as h approaches 0 back in for our answer. All right, and this is going to be the step that we're going to be doing every single time. So we always want to get rid of all of the x's. Again, if we're ever left with an x that does not have an h, it means that we've done something wrong because it will always, always, always work out. So get rid of all of the x's, factor out an h, get rid of it, plug back in. We'll always get an answer. But here, it's not very straightforward. So if you remember, I believe a couple lectures ago, we were solving limits that looked something like this. And we had this idea of if we had any form of a square root and we were looking to solve a limit, we had to use this idea of the conjugate. And what that is, oops, is we need to take the term with the square roots and we're going to multiply by a fraction. And we're multiplying by the conjugate. And the conjugate is just changing the sign in between the two values, the two terms that we have involving the square root. All right, so here we have the square root of x plus h, and we're going to make sure that we're not changing the sign under the square root. We're just changing the sign between whatever the terms that we have are. And we have the square root of x. Since we have a minus here, we're changing this to a plus. But since we are putting this into the numerator, we also have to put this into the denominator, because otherwise we're changing our expression and we can't do that. All we can do is manipulate it. This is a fancy form of 1, so we're actually okay. And I also mentioned before that what we want to do is we only want to distribute the term that has the conjugate. So I'll rewrite that. Only distribute term with conjugate. And the reason for that is that the term with the conjugate is going to actually simplify to be something that we need to cancel out in the other side. So whether the conjugate's in the numerator or the denominator, it doesn't matter. It'll cancel out with something from the opposite side of the fraction that we need to cancel. If you factor out everything in both sides, it's going to be a problem because you're not going to be able to cancel anything. All right, so let's go ahead and multiply out the numerator. So we have the limit as h approaches 0. And we said this is a difference of perfect squares. So technically, all we have to do is multiply the first two terms together and the last two terms together. If you wanted to FOIL the whole thing out, consider that there should be parentheses around both of these like this, same here. You can, and you'll see that we get the same exact answer. So we'll multiply the first two terms, but when you square a square root, they both go away. So you're just left with what's under it. So you get x plus h. And then minus, so minus times plus is minus, square root of x times square root of x is square root of x squared, but square root and square are inverses that go away. So we're just left with the thing under the radical over, and then this is where we do not touch the thing that was not the conjugate. So x plus h plus square root x, we're just going to leave that, and we'll see exactly why when we simplify our numerator. So we have x minus x. We notice that this rule up here that says that we need to cancel out all of our x's does in fact work because we're just left with an h over h times this whole mess here, x plus h plus square root of x. And then we can cancel out our h's. Be careful when you cancel out everything from our numerator or our denominator. We are still left with a number, and the number is just 1. 1 over the square root of x plus h plus the square root of x. Once we cancel everything out, we can go ahead and try to plug back in with our limit because the issue was that h in the denominator, but we've gotten rid of that. So we can go ahead and plug in. So we plug in 0. Well, that goes into the square root of x. So we get 1 over the square root of x plus the square root of x, but that's just 1 over 2 times the square root of x. Because x wasn't a specific value, we weren't looking for the limit at a specific point. We were just looking for the general limit. This is our answer. That is the derivative of the function. So you plug in any number for x, you get the slope at that specific point in the function. All right, let's go ahead and try another one. So now this one is going to require a little bit more work because we're squaring things in distributing terms. So we will once again rewrite limit h approaches 0 of f of x plus h minus f of x all over h. And again, we don't actually have to rewrite f of x because we're given f of x. Yay. So now we actually have to go ahead and just do f of x plus h, which is going to be quite long. So f of x plus h equals. Now again, for x plus h, we go ahead and plug x plus h in everywhere we see an x in our function or whatever variable we have. So this turns into x plus h squared minus 2x plus h. But we need to simplify this. So from a previous lecture, we remember that this x plus h squared is the same as x plus h times x plus h. And if you go ahead and distribute that, what you get is x squared plus 2x h plus h squared. And I encourage you to confirm that if you are not convinced. And then we can distribute this guy here, distribute the minus 2 to both the x and the h, so we get minus 2x minus 2h. So this is the fully simplified numerator. There are no more terms that we can add together. So we're just going to go ahead and put this right in for x plus h. So now this is equal to the limit as h approaches 0 of f of x plus h, which is this really ugly looking thing here, x squared plus 2xh plus h squared minus 2x minus 2h minus. Now this is where parentheses are very, very, very important. Because if you just subtract the first term, we are missing a negative in the second term. So we subtract the whole thing minus all of f of x, which is x squared minus 2x, all over h. But now we have to go ahead and simplify that. So let's do that before we go ahead and cancel anything out. X squared plus 2xh plus h squared minus 2x minus 2h. I'm just going to distribute my negatives. So this is minus x squared plus 2x all over h. So once we get to the point where we are now just looking at a string of terms, no parentheses, we can go ahead and try to cancel out anything that has an x, and it should work. So first we see x squared minus x squared. Those two things can go away. 2xh, that's fine. H squared, that's fine. Minus 2x plus 2x. Those two things do add to 0. Minus 2h, that's fine. Nothing else goes away. So now let's go ahead and rewrite what we have left. So we have the limit as h approaches 0 of 2xh plus h squared minus, this is a 2h all over h. And this is where we see there's an h in everything. So we can say this is equal to the limit as h approaches 0 of, well, we could factor the h out. So we have 2x plus h minus 2 over h. And just like that, we again cancel out the h. So this is how we've confirmed that we've done it correctly. So this is equal to the limit as h approaches 0 of 2x plus h minus 2. And the last step is just going to be plugging in 0. Well, here's an h. You plug in 0, you just get 2x minus 2 for your answer. And again, this is the general derivative. And so we'll call this equals f prime of x. That is your general derivative. And I'll do the same thing for this one. This is your f prime of x. This is your derivative function. All right, so while I could call it f prime of x, if you look in our textbook or if you look at really any other resources, any other videos, anything like that, there's a lot of notation when it comes to derivatives. Calculus has been around for a long time, so they introduced a lot of notation and it's just kind of stuck. So here's a couple different ways that we can see the same exact idea. So again, these are all the same thing. So this is f prime of x. This is the derivative. You could see this idea of dy over dx. So this is read as the derivative of y with respect to x. So that's kind of how we would read that. Typically we say dy dx, but it means the derivative of y with respect to x. We could also say y prime. So if instead you're not given f of x, you're given y, then instead of f prime, you can just say y prime. You can also, instead of dy dx, so the idea of why it is dy dx is if you have some function that's like y equals, let's say, the x squared from before, you want to take the derivative. Well, a derivative is d over dx. This is saying we're taking the derivative with respect to x of this, which means that we're taking the derivative with respect to x of this. Essentially, we're just going to take this y and move it into our numerator. So dy dx equals, and then from before, x squared. Oh, we haven't done this one. So this we will do at some point. This is just going to be 2x. So this is the idea of how we're able to kind of rewrite the d dx here as dy dx if we're given a function y. So if we're given d dx of f of x, we're not necessarily going to write d f of x up here. You're probably not going to see this one quite as much. Sometimes if we're asked to evaluate at a specific point, so kind of what we were doing in the last lecture, instead of f prime of a, you can see this bar. So this is called an evaluation bar. And what this means is the derivative evaluated at x equals a. So evaluated at x equals a. So that means go ahead, find the derivative, do everything that you normally do, and then at the end, plug in a. All right, you'll see this quite a bit a little bit later on in the course, and if you take Calc 2, you'll also see this in Calc 2. All right, and this is a little bit more of a visual representation of the derivative. So dy dx is the slope, right? Derivative is slope. And so slope, if you think about it, is change in y over change in x. So the limit as the change in x approaches 0, which is just your denominator, is this thing right here. So this is a nice little visual representation of like kind of confirming that what we're doing is in fact exactly what I'm saying. All right. Now we're getting to a slightly stranger concept. I know calculus is often a little bit harder to wrap your head around because when you're going through math in high school or even pre-calc, it's stuff that you've kind of seen before and you're just kind of building on that. But calculus is this whole new concept where we're introducing this idea of a derivative, and most of the time you've probably never seen this before. So now I'm asking you to sketch a derivative given a function. And this is kind of weird. So first of all, let me kind of explain how this works. So if we know that slope is the derivative, so derivative is slope. So the slope at a point, it would help if I could spell. That's okay. I do math, not English. So the slope at a point is the y value of your derivative. All right, and let me illustrate what I mean. So what we're going to do is we're going to choose a bunch of x values. We're going to determine what we think the slope is. This is really just kind of an estimation game here. We're going to determine what we think the slope is, and then we're going to plot that value. So what I'm going to do is let's maybe take a look at -3. So what we're going to look at is the tangent line. I'll put in parentheses here, tangent line. And if we draw a little tiny tangent line, what we're going to do is we're going to estimate what we think the slope of that is. First of all, that's negative. So this is negative. I'm going to say maybe -1/2-ish. This is totally a guesstimate. So at -3, I'm going to say f prime of -3 equals -1/2. All right, now I'm going to go -2. I'm going to draw a tangent line. and that's a horizontal line. So f prime at -2 is 0. The slope of a horizontal line is 0. That's like you're walking on flat ground. There's no slope at all. There's no increase. Now we're going to look at -1, draw a tangent line. Again, I can't draw, so these lines are just awful. Sorry, guys. When we draw our tangent line, I'm going to say maybe that's like, I don't know, 1. So f prime at -1 is about 1. All right, since this looks pretty consistent, I'm going to kind of just make a little jump. I'm going to say, what about 1? I'm going to skip 0 because it's about the same. I'm going to do a little graph. I think it maybe looks a tiny bit steeper, so I'm going to say f prime at 1 is maybe 1.5. Now I'm going to look right at the max here. If I drop this down, it looks like maybe 3.5. So f prime at 3.5 is, well, if we draw a tangent line, what we see is that that is another horizontal line. So that's 0. And then if we go to, say, 5, we draw a tangent line. What we get is another very decreasing slope. This one is more negative than this one, if you see. So I'll call that one maybe -1. So f prime at 5 is -1. All right. And this honestly is probably enough to go ahead and try to graph. So now let's choose a different color. Let's go purple. I don't think I've used that one. Now I'm going to go ahead and plot these points. So at -3, we're at like -1/2. So -3, -1/2 right here. -2, 0, -1, 1, 1, 1.5, and then 3.5, 0, and then 5, -1. And we see that this is probably just going to get more and more negative. And we assume that this is going to be a continuous function. So we're going to draw arrows at the end of it. So I'm going to go ahead and connect my dots. And we're going to pretend like that went through that. And this is f prime of x. So just like that, we were able to graph the derivative function just by looking at the original, by looking at the slopes of the original function. And what I really want to note here is that, first of all, we see the maximum and the minimum. So this is a local minimum and this is a local max, occur on the derivative function as zeros. So local min slash maxes are zeros on the derivative. All right, and that's going to be always. This is something that is going to come back a little bit later on in the course. We're going to be spending quite a bit of time on this, actually. And then what you notice is to the left of this, you notice, so we always read a graph from left to right. So considering that this goes on forever and ever, this is a decreasing function until we get to -2. In the derivative function, you notice this is a negative y value. Now, in derivatives, we don't necessarily care about increasing or decreasing. What we care about is positive or negative. So this is decreasing until -2, and this is negative until -2. In the original function, between -2 and I'd say about 3.5, we're increasing. And you notice that is the only positive part of our derivative function. And that's not a coincidence. So increasing implies a positive y value on our derivative. Decreasing implies a negative y value on our derivative. Again, we'll see here we're decreasing from about 3.5 until forever. And so here we hit our x and we're decreasing, we are negative in our derivative function forever. All right, so I can put this as a note as well. So increasing f of x implies, so any the two arrows, the little arrow here just means implies. Increasing f of x implies positive derivative y values, and decreasing f of x implies negative derivative y values. And again, this is always, so this isn't like this specific function. This is a generalization that will hold always. All right. Now we're going to kind of come back to talking about differentiability real quick and continuity. And so this is just kind of a little visualization of the difference between being differentiable and being continuous. So what this is telling us here, what this theorem is telling us is if f of x is differentiable, then it is continuous at a specific point. Now, the way that if then statements work is that if it says if here and then here, you can't necessarily flip it. You can flip it if it says if and only if, but this doesn't say that. So if you were to say a continuous function is differentiable everywhere, that would be incorrect because that is not true. And we'll see an example in the next slide. So what this diagram is showing is that every single differentiable function can be contained within the idea of continuous function. So if you're differentiable, you're immediately continuous. But if you're continuous at a point, it doesn't necessarily mean you're differentiable. So maybe you're like over here, and that's not a differentiable function. All right, that's just a visualization of it. So let's take a look at what it means to be continuous versus differentiable. So here we have an absolute value function, right? So this just looks like a V, it hits the origin. And we want to know if this is continuous and if it's differentiable. Well, we know to be continuous means that for every x value you plug in, you get a y value back. We know there's never going to be a value that you plug into an absolute value that you don't get a value back. Absolute value just takes negatives and makes it positive. So you plug in any negative value, you get the positive out. You plug in a positive value, you get a positive out. You plug in 0, you get 0. So therefore, this function's continuous forever. But the question is it differentiable everywhere? And the answer is actually going to be no. So let's see why. So is the function continuous? Yes. Is the function differentiable? So the function is differentiable everywhere except for one point, and that one point will actually be at the corner. So we have specific functions that have certain properties. So this is actually called a corner. I mean, it looks like a corner and it's called a corner. And the reason why it's not differentiable is because of the idea of a limit. So we know the definition of a limit is in order for the limit as x approaches a of f of x to be equal to L, that means that the limit as x approaches a from the right of f of x must be L, which also must be the limit as x approaches a from the left of f of x. All right. But if we're looking at what this actually means, we take the limit of our function. So we know we're looking at 0. This is going to be the problem area. So we're going to use a specific variation of the limit definition just because it's easier. So f prime at 0, we take the limit, plug it in. Well, 0, the absolute value of 0 is 0, x minus 0 is 0. So what we have as the limit as x approaches 0 is the absolute value of x over x. But what it means to be an absolute value is that you can have a positive or a negative. So coming from the left, this is how we'll think about it. The limit is the derivative of the function. What we're doing here is taking the derivative. So if we're looking at the slope, since derivative is slope, well, what is the slope of an absolute value function? The slope coming from the left, slope, here is -1. We are going -1 until we hit 1. It is consistent until we hit 1. And what is the slope from the right? Well, from the right, the slope is +1. Again, until we hit 1. And there's no nice little curve like in a parabola that might go like this. There's no nice way of transitioning into the +1. It goes immediately from -1 into +1. It's like a little jump. And that's what we see here. The limit as x approaches 0 from the left is -1. If you tried plugging in numbers into this absolute value, that's exactly what you'd wind up with. And the limit as x approaches 0 from the right is +1. But that doesn't satisfy the definition of a limit. A limit says that it has to be the same number. Therefore, because it's not the same number, the limit doesn't exist, and it's not differentiable at that point. So is the function differentiable? The answer is yes and no. So not at x equals 0, yes everywhere else. And the reason is if you take this random point here, the limit coming from the left and from the right is going to be the same exact value, whereas here the limit from the left and from the right are going to be different. We also have something called a cusp, which I don't think I have on these slides. It's kind of harder to see this example. I don't know if we will. We have something that's a cusp, which is a straight line, and then it kind of comes up like a curve like this. So now this corner looking thing here is not a corner, it's called a cusp now. So this is also not differentiable. Specifically at the cusp. It'll be differentiable everywhere else, but not there. So if you see a function that looks like this, where it's an immediate transition from a line into this kind of curve, that is not differentiable at that specific corner cusp. All right, there's another spot that we'll be looking at, which is right here, in which we will not have differentiability. So here we have a function that is a pretty common function. So this is going to be the cube root function. The cube root function just goes down forever, comes up, hits our origin, and then goes to the right forever. And you may look at this and originally just based on looks, you'd say, oh, this is differentiable everywhere. It's continuous and it's differentiable everywhere. But in order to be differentiable everywhere, you can't have a vertical tangent. You can't have what would be like a vertical asymptote type deal. So to be differentiable, your limit cannot be infinity. You can't have that infinite discontinuity. Well, it's not a discontinuity necessarily, but you can't have an infinite limit. So if you tried to see if it was differentiable at 0, you could do f prime at 0 and plug it into the more specific definition of the derivative that we have. And what you'd wind up with is 1 over the cube root of x squared. And the way that we get that is using our rules of simplification using exponents. So I can go through that really, really quick. We have a rule that we went through in the beginning of the course that says if you have like x to the m over x to the n, that's equal to the x to the m minus n. We have two bases that are the same. So what we could do is we can convert this root into a fractional exponent. And so we have this rule that says if you have the nth root of x to the m, you can write this as x to the m over n, or what I like to think of it as is x to the power over root, where the power is just the thing attached to the x. It's like literally the exponent, and the n here is the root or the index of your root. So what you would do here, I'm just going to rewrite it off to the side, is to rewrite the cube root of x. First, we have to consider what is the power. Well, if we don't see a number, it's immediately a 1. And so to rewrite as a fractional exponent, this is x to the power, which is 1, over the root, which is 3. So now we have x to the 1/3 divided by x. But x, again, is x to the 1, which if we wanted to write that in a fancy form, since we know we're going to have to subtract that, we can write that as x to the 3/3, because when you divide that, you get 1. So therefore, we know that this is x to the 1/3 minus 3/3, which is x to the minus 2/3. And again, you may look at this and say, well, that's not what we're looking at. And so what happens is we can rewrite this first by getting rid of the negative. We had a rule that said if you have x to the minus n, you wanted to rewrite this to have a positive exponent, you had to flip the fraction. So here you could rewrite it as over 1. This turns into 1 over x to the positive n. So this could be rewritten as 1 over x to the 2/3. And you may be looking at that and say, well, that's still not this. Well, we can go backwards from the rule that we have here. So if you know that you have a power over a root, you know you have a fractional exponent, you can go back and put it in power over root form. So this is 1 over, this is some sort of a root with this base. Well, 2 is the power, 3 is the root. So that's just how we get this number here, if you're curious. So now if you go ahead and try to plug in 0, you get 1 over 0, which is a problem. And through some other differentiation rules, we find out that the limit is actually just going to be infinity. So we get what's a vertical tangent right here, which tells us that this is not differentiable at 0. All right. So this is another type of question that we may see. We like to ask questions about something about continuous and differentiable. And a lot of times that will come in the form of piecewise functions. So in order to be continuous and differentiable, we know the two pieces must connect. So they must have a closed circle there, and they must connect so that this function Essentially, if you put your pencil down, you could just continue on forever without ever having to lift it up because there's no holes, there's no jumps, there's nothing like that. So we're looking for an A and B such that that is true. Well, we know that we're looking at 3. Here we have x squared, and we have ax plus b. So first of all, if we need them both to be continuous and differentiable at 3, we know that one of them has to be x squared. So if x is 3, we can just plug that in. So x squared is, well, 3 squared, which is 9. So we know that this function here is going to be equal to 9. We know also, like I said, in order to be continuous and differentiable, that these two guys have to be equal. They have to connect so that it's a nice continuous function. So I know that ax plus b must be equal to x squared. At 3, this is the same thing as saying we'll plug in 3. 3a plus b is 9. Now, we don't necessarily have any other linear equations or anything to use like substitution or elimination or any of the rules that we may use. But we're just finding values of a and b that would make this true. Well, there's actually pretty much infinitely many values that that would take this form. So just choose some values. Which a and b can we choose to make 9? Okay, well, what about a equals 3 and b equals 0? So 3 times 3 plus 0 is 9. What about a equals 2 and b equals 3? 3 times 2 is 6, plus 3 is 9. What about a equals 1 and b equals 6? That works too. 3 plus 6 is 9. You can go on forever. So we're just finding some values that would make this true. If you were looking for specific values, you'd be given a little bit more information. But any of these values work. And again, if you came up with values that weren't these, but it satisfied this equation, that would also work. Now, we also have this idea that I may have mentioned in a previous video that we might not just want to take the first derivative of a function. And in fact, there are some really cool applications when we are taking more than one derivative of a function. So this is the notation similar to how we had before of higher order derivatives. That's what they're called. So if we're looking to take the second derivative of a function using the typical f prime of x notation coming from f of x as a function, the second derivative is f prime of x, so this is second. The third derivative is f triple prime of x. And then once you get past 3, that would be absolutely insane to try to write as many primes as you need. So we just start putting in parentheses the derivative. And it's important that we put it in parentheses because otherwise you may mistake it for an exponent. This is not an exponent, this is a derivative. And this can go up to the nth derivative of your function, where n may be unknown. Same thing with y, maybe you have y instead of f of x, y prime, y triple prime. And this is the slightly more confusing notation. So if you have y and you take the derivative with respect to x of y, this gives you dy dx. But if you try to take another derivative, so you take the derivative with respect to x of dy dx, what do we get? Well, what we actually get is d squared y over dx squared. I know the notation looks a little bit funky, but this is saying we're taking the second derivative with respect to y of our x value. You don't need to plug in anything else crazy for this. This is just notation. All right, so if you see any of this, that's just what it means. All right, so let's go ahead and try to find the second derivative. We are coming to a close for this lesson. I think we have one more after this, so let's find the second derivative. So once again, we have the limit as h approaches 0 of f of x plus h minus f of x all over h. We know what f of x is, so f of x plus h is x plus h squared, which we know is x squared plus 2x h plus h squared. So this turns into the limit as h approaches 0 of this guy here, which is x squared plus 2xh plus h squared minus f of x, which I don't need to put parentheses around because it's a single term, just x squared all over h. And now we don't have to distribute, makes it way easier. We can just cancel out any terms that we have that are going to be adding to 0, which are x squared and minus x squared. These two guys you can't combine. So we get the limit as h approaches 0 of 2xh plus h squared over h. Well, we can factor out an h. So this is the limit as h approaches 0 of factor out an h, 2x plus h over h. Would you look at that? We can cancel out our h. So this is the limit as h approaches 0 of just 2x plus h. Now this is just a linear function, which means that we can go ahead and plug 0 back in, and we just get 2x. This is f prime of x. All right, but we're not looking for f prime, we're looking for f double prime. So to get the second derivative, it is just the derivative of the first derivative. So f double prime of x equals the derivative of this, which is the limit as h approaches 0 of, we'll say, f prime of x plus h minus f prime of x all over h. Let's do it again. So now f prime of x plus h is, it's just 2x, so that's 2 times x plus h, which is 2x plus 2h. Pretty straightforward. So let's plug this in. This is the limit as h approaches 0 of 2x plus 2h minus f prime of x, which is just 2x, all over h. And we should once again have all of our x's canceling out. 2x minus 2x is in fact 0. We get the limit as h approaches 0 of 2h over h. And we don't even have to do anything here. The h's just cancel out. We get the limit as h approaches 0 of 2. And if we remember, this was actually a limit rule. It says the limit of a constant is just the constant. Therefore, your answer is just 2. This is your f double prime of x. So that's your answer. And you can find however many derivatives you want. If you tried finding the derivative of this, you would actually find out that it's 0. Pretty fun. All right. So now we get to the fun stuff. This is our last slide of the day. So this is more of the real world applications of what we're going to be looking at. So a lot of times what we'll have in terms of real world applications is we're going to have specific names of the functions, which is going to look something like s of t. And that is our position function. I think that I may have mentioned this already, but this is more of the formal way of showing you everything all at once. So this is important to know right here. Maybe not these last guys, but this is all very important. Well, maybe not even this one. Up to here. You definitely need to know up to acceleration. Jerk is just kind of for fun. So s of t is your position function. That's just like if you're given like an f of x. That's just a regular old function that tells you where you are given some x value and maybe some height or something like that. When you take a derivative, we mentioned this in the last video, you actually get a velocity function. So the first derivative of the position function is the velocity function. So we can immediately call that v of t. Now, I also mentioned if you take the derivative of the velocity function, you got something cool. And that cool thing is the derivative of velocity is acceleration. So that means the second derivative of the position function, which is the first derivative of the velocity function, is the acceleration function. So you may be asked to find any of these things. And also, if you take Calc 2, you'll be asked to go babackwards from here. So Calc 1 is kind of about taking derivatives. Calc 2 is about going backwards from derivatives. So finding the original function given a derivative. So you'll be given an acceleration function and be asked to kind of reproduce the position. But right now, all we have to worry about is given some position function, maybe we'll be looking to find the acceleration function and then find the acceleration at a specific point. The rest of these are maybe just for fun. Mathematicians just like to have fun sometimes. I don't fully know the story behind the jerk function. This is the third derivative of the position function, which is the derivative of acceleration. It's called jerk. Don't ask me why, I don't actually know. And yes, believe it or not, the fourth, fifth, and sixth derivatives of a position function are actually called snap, crackle, and pop. Mathematicians need to have fun somehow, and apparently this is how. I remember when I was first told this in high school, I genuinely didn't believe my teacher, but this is true. They also have other weird names. If you are curious, you could look them up. But yeah, so anyway, these are the Rice Krispies of derivatives. So that's all for today. If you have any questions, let me know, and I will see you for our next video.